Recorded rolling. It's Thursday, November 13th. So most of the energy quizzes I have turned in. So just wait a few more of those. Your circular motion gravitation quizzes are back in your folders. You guys have those. So if you want to do corrections at some point, you can. Yesterday, I took you guys through this page. So this week we've been doing momentum. These are some very fundamental momentum questions. I did solve a couple of these with you guys, but for the most part, I showed you guys how to set these up and solve these, or think about them. Now, some of you guys did finish this in class yesterday and already turned it in. Some of you guys might have like 2 or 3 left. So I'll just do tomorrow, and then I will get this in the gradebook then. If you already turned in, and I'm already starting to sort these and put these in. We're coming up on the end of the interim, so all your teachers this weekend are going to put grades in the grade book and get all those up to date for the interim. Right. A few AP notes. So AP, there's AP classroom due Monday, so not for honors, just for AP. Also for AP, I have your momentum puzzles together, so it's chapter 9. So I just put these in your hands today. So I think I want to do the same thing with these I did for the last couple chapters, which is we'll save a day next week to just do some of these in class, and then whatever we did in class, I'll just have you guys turn in. Okay. But of course, you can always read these ahead of time. Be thinking about these. If you need some extra examples or some like college level examples, then have these in your hands now. See how those. Okay. I'm working up towards the Inelastic collisions lab, so I want to tell you guys a bit about that. Okay. But I've got one more AP detail, which is I want to update with you guys this AP equations page. So where are we here? We got kinematic motion, here's dynamics, there's circular motion, gravitation, and then energy is all these in green. Okay. So my posters for momentum have blue banners, so I'm going to use blue. Okay. It's all these down here at the bottom. Okay. So if I hold this up, you guys can kind of see this. Okay. Okay. Oh, there's P equals mv. You guys see? Can you guys read that as momentum is mass times velocity? Look, they even gave you the little vector arrows above those. Okay. All these I'm going to go over right now with you guys. So I'll go ahead and circle them. Okay. And then this is going to be momentum right here. All right. So I'll write momentum. Okay. Now, when I hold this up to the camera, sometimes it's hard to get it not blurry. So here, I'll write up the other ones. So the next one says this. It says F net. They even put a vector arrow above the force. Okay. Equals, here's an interesting perspective that I hadn't explicitly gone over yet. It says the rate change in momentum. So change in momentum over change in time. Because if there is a net force on something, there would be an acceleration and it's changing its velocity. So there would be a change in momentum. Okay. So, okay, so that's interesting. And they rate it further this way. You guys know momentum is mass times velocity. So change in momentum could be mass times change in velocity, as long as the mass stays the same. Usually the case. And what do we have here? Guys, what's change in velocity over change in time? What's that called? Acceleration. Hey, F equals ma. Look at that. It was Newton's second law of motion the whole time. The skies. Get that? Look at that. Newton's second law. Now, right beneath that, it says J with the vector arrow equals force average times time interval, which is also called delta P. Guys, what was I calling this yesterday? It starts with an I. Impulse. Yeah, thanks. Yeah, you guys remember impulse is a change of momentum, which could be mass times change of velocity, like up here. Okay? And you get that by applying a force for some time interval. And if you saw a graph that was force versus time, it would be the area and curve, wouldn't it? Okay. So this capital J, I hadn't seen it in a few years, but AP just updated their equation book, I think about a year ago, and they brought back the capital J. So if you ever open the physics textbook and you see a capital J, they're probably talking about impulse, change of momentum. You might see that. Okay, and then this last one says velocity for center mass is the sum of momentum divided by the sum of masses. Okay. Which reminds me a lot of center of mass, like as a static point. You guys remember center mass is like a weighted average of the masses, mass times location, all divided by sum of masses gives you the average location. Right? Well, this is really the same idea. It's just putting it in motion because momentum is mass times velocity. So the average velocity. Suppose you have like 2 objects, or maybe like 10 objects, or whatever you have. If you find what's the sum of momentum for all the objects divided by the masses, it'll tell you what the center mass is doing. Okay, good. And I do have a few posters that are related to center mass. You guys saw these earlier this week, but just to remind you guys. Suppose you have two asteroids colliding, and you focus on not either individual asteroids, but the center mass of the two asteroids. Would you ever know when the collision even happens? No, you have no idea. Is that true if it's elastic? Yep. Is that true if it's inelastic? Yep. Is that true in 1 dimension, 2 dimensions, 3 dimensions? Yep. That's always true. One that was related. You guys remember the magic school bus question?
Yeah.
She threw the ball and then scooted back for second base because there was a frictionless baseball field. Sometimes you see it phrased as an icy pond. Okay? So, so same idea, but this is more like an explosion type example. Okay. And then, remember this one too? If you throw a grenade and that's a dud, maybe it lands pow right here. But if it explodes into 2 parts, a million parts, whatever, the center mass also lands at that exact same location, as if it had never exploded at all. So the explosion does not affect the center mass. Just like this throwing the ball does not affect the center mass of the ball personal system, just like this collision, the center mass is not affected by the collision. Right, so one more I'm going to circle. Are you guys good with those down bottom? Right. It's the only one that I have unmarked so far on the left side, which is this right here. It's the center mass. Now, every physics textbook decides where it wants to put those. So some put it in, AP put it right under kinematic for some reason. I'm doing this kind of with momentum. Right, and then this will also be important in rotational dynamics. This is your center mass right here, which is just this one right here. Okay. All right, so you guys go with the AP equation page. Okay there. All right, so what we're doing today is this inelastic collisions lab. Okay, so you guys have these low friction parts today. Now I only have one for the video, but back there you'll have pairs of parts that can collide into each other. Now, because what does inelastic mean? It means that after they collide, they do what? They stick together. And that'll happen because I did tape some of these bar magnets on the front, so they'll stick together. They'll stick together like that. Okay. So here, I'll go to the table with you guys. And today's lab is really just kind of exploratory. You can change whatever variables you want. You can change masses. You can change starting speeds. I just want you guys to gather a bunch of empirical data and then see how does that compare to what I've been claiming, how this collision should work. Momentum should be conserved and so. So you got trial A, B, C, D, E, 1, 2, 3, 4, 5, whatever. So you got 2 carts. Because what is the mass of an empty cart?
500 grams.
500 grams. Yeah. Because what is that in kilograms? Yeah, 0.5. Notice I have a lot mass listed in kilograms, and each velocity is listed in meters per second. Because what if I do this? What if I take a 1 kilogram mass and clunk, put it there? Now, what's the mass of this whole system?
1.5.
1.5 kilograms. You guys get that? So you can very easily change out mass. You have lots of weight. You have 2 carts. I do have some speed gates back there. So you're keeping track of these velocities. So anything pre means pre-collision. Anything post means post-collision. So you might have 2 individual carts. Now, could you simplify this by having 1 cart to start at rest? Yeah, you could do that. In which case, maybe the cell could be 0, right? Or if you want to roll into each other, you can also do that. But now you've got an extra velocity to keep track of. Might be a little trickier, but maybe you can figure that out. Right? So what's the velocity of each cart before the collision and then after the collision? Okay. That'd be in meters per second. Oh, how about this? Because if you did have them rolling towards each other, which you might want to try that, then if one has a positive velocity, would the other have to have a negative velocity? Yeah, you have to record that as a negative number. Okay, so just watch for that too. If you have opposite directions with momentum, because momentum is a vector quantity, so it is important to keep track of the direction. Right versus left could be positive versus negative. Okay, guys, what's the unit for momentum?
P.
Measured in. Okay, yeah, the variable is called P. Is that measured in kilogram meter per second? Okay, because I'm telling you, momentum is constant velocity, kilogram meter per second. You guys see that? Okay. There's no special name for that unit. Just call it kilogram meter per second. Okay. Do you guys know how to calculate this? Okay, you just take this mass times this velocity plus this mass times this velocity, add it all up, and you get the pre-collision momentum. Okay. Guys, what about this? What do you got? You have 2 carts headed toward each other, and one has positive 12 units to the right, and the other has negative 12 units because it's going to the left. What's the total momentum in that system? 0. So in that case, numerically, you better get 0. And what do you think would happen once they collide?
Stop moving.
Yeah, they should stop altogether. Of course, you guys can try that out today, because today's the science day. Right? You guys get to do some experiment. Right? So momentum is mass times velocity. P equals mv. So some version of that. Add it all up. Okay. Guys, what's kinetic energy? How do you calculate that? 1/2 mv squared. Great. Now, if you have two individual parts, you could calculate the kinetic energy for each one and then just add it together. Okay. Oh, guys, will you ever end up with a negative term for kinetic energy? No, it'll always be positive. Because even if you have a negative velocity and you square that, it's still positive, isn't it? Okay. Remember, energy was a scalar, so it just adds. Okay. And that's measured in what unit? Joules. You guys remember joules? Right? Joules for kinetic energy? Or energy in general? Right, you guys remember that? Okay. Right, so I think you guys have a good amount of time today to get a bunch of data. On the back side of this page is a general collisions lab. General collisions looks fairly similar. The difference is that actually these carts do have magnets already built in, so they'll bounce off each other. Like boing, boing. They bounce off each other pretty elastically, actually. Okay? So post collision, you do have to keep track of two independent velocities, which is a little trickier. Do you guys think you can come up with a way between today and tomorrow to figure out how to do that? Right. Okay, so I'll let you guys think about that. You have about 1 day to think about that. Okay. Now today, of course, you guys got speed gates. Do you guys also see some markers taped to the carts? Right. Now one marker is about 9 grams. I don't think it'll change that much anyway. But if you wanted to measure, there's a triple beam balance back there. You can always measure these with that triple beam balance. Okay. So there are a lot of markers taped back there. So that the marker can go through the speed gate, zoop, and then it can read the speed for you. Okay. All right. So go ahead, just get lots of data today. You can change out masses, you can change out velocities, just play around with this. The momentum ideally should be conserved. See how true that is. What should happen to kinetic energy?
It should 1/2.
It should decrease going from before to after whenever you have an inelastic collision. See if that's also true. Okay.
Provided so much, any type of energy